Hello and welcome to lesson 10.3 on solving exponential and logarithmic equations. Now, I love this stuff. I really love this. This is where we really get to put everything we've been doing all year into practice here. Oh, it's fantastic. It's so great. So, we're going to talk about how to solve exponentials and logarithms. You could be given a logarithmic equation, you could be given an exponential equation. What do you do, right? Well, how do you do this? Well, this is where I don't have as much structure as before. It used to be like, oh, well, if you have a quadratic equation, set everything equal to 0 and either use quadratic formula or factor, right? And it's very, you can use whatever, you have a framework to really go off of. Here, you still have some frameworks you could work off of, but a lot of it is just creativity. It's playing around with it. It's just using algebra to have fun with it and solve. Here, I've got a few things. So here's that classic conversion between log and exponential. We've covered that in 2 videos now, but there it is again, okay? Something new. I would star this. In fact, I'm going to do that in yellow for you right here. Same base rule. This is an important new thing to know. The same base rule it says exactly this. If you have b to the m equals b to the n, then the exponents have to be equal. So look, if I have, 2 to the x equals 2 to the 3, then what does x equal? X equals 3. Right? If you have the same base, the exponents have to match, right? They have to, okay? That's all the same base rule says, but we're going to see that rule in action a little bit later, okay? It's very useful sometimes. But I'm going to go through a variety of methods and ways of thinking to solve these problems. And I'll tell you this, almost all of these examples, you can find another way to solve it, using other techniques from other examples, okay? All I'm really doing here is illustrating different techniques and ideas and just showing you how to think about it, okay? So we're going to use a combination of stuff. We're going to convert between exponential and log. We're going to use the properties of exponents and logs. That's all of this stuff. You got to know these, all of them. Maybe not those, it's okay. But you got to know those for sure. Use of the same base rule, which is this thing I put up here. Old school factoring patterns. You got to know, you still got to remember how to factor. We're going to see what factoring looks like here. It's awesome. And then a new thing, taking the log of both sides. And I put a little note here. I usually use natural log, but a log of any base is acceptable. I'm going to show you what that means. What does it mean to take the log of both sides? I'll show you exactly what that looks like, okay? Think of it like this, right? If you had x squared equals 4, how do you solve both sides? You take the square root, right? We can do something similar. If I said 2 to the x equals 10, you could take the log of both sides. Does that make sense? You could take the log of both sides and use that to solve. Okay? Okay. How will you know which one to use? I would read the question. It might give you a hint, or really just carefully look at the equation you're given. Think about what the equation tells you, what information you have, and what techniques you might be able to use to solve. I could ask you to solve a problem in a variety of methods. I might give you the same problem, say, hey, solve it 2 different ways. Or I want you to solve it this way. Can you please demonstrate that you understand how to use this solving technique? Okay? All right. I'm going to try and keep this video as short as possible, but I also want it to be sufficient in explanation because this is going to get really tricky. So I'm sorry if the runtime is a little bit long, but I really, really want to explain this one well, okay? I just want to explain it well as best I can. Okay, example 1. And I put the technique as the subtitle for every example. We're going to solve this exponential by just typical conversion to log form. Now to do this, all you need to do is isolate your exponential. So I'm going to say isolate exponential, okay? And then you can convert. So what is my exponential term here? It's 5 to the 3x plus 2. So this is the thing I want to isolate. So I'll subtract 5 from both sides. I'll get 5 to the 3x plus 2 equals 6 minus 5 is 1. And now I'll convert to log. And the base is 5, right? So I'm using this rule right here. It's the classic conversion. The base is 5, the argument is this, blah, blah, blah. So I should see that log base 5 of 1 equals 3x plus 2. Now, seeing that, I'll tell you this. Sometimes, and you know what, now I'll add that comment later. Sometimes you can evaluate this logarithm by hand. Sometimes you can't. Sometimes, if I said log base 5 of 2, you actually can't evaluate that by hand. You need a calculator to do an approximation. In this case, log base 5 of 1 is 0 because, right, maybe I could put this in yellow. I say log base 5 of 1 equals 0 because 5 to the 0 equals 1. Okay? And you probably could have noticed that at this step. You say, well, when is 5 to the power of something going to be 1? It's going to be 1 if the exponent is 0. But you may not have noticed that initially. If you did, congrats. You didn't actually need to do this, but whatever. Okay, so what I get here is that 1 equals 3x plus 2. I'm sorry, no, 0. What am I doing? Sorry, because log base 5 of 1 is 0. So 0 equals 3x plus 2. Let's quickly solve, right? Negative 2 equals 3x. Divide both sides by 3. Therefore, x equals negative 2/3. Okay. And we are done. I would sometimes, it's a good idea to check for extraneous. Sometimes we are going to have extraneous solutions. I'm not going to bother doing that in this video, though. I don't think we need to check for extraneous on any of these. Maybe we'll talk about that in class, about when you need to do that. Okay? I mean, you should always really be doing it, but yeah. Okay, so that's example 1. Simple enough. Example 2, let's solve a log by converting to exponential. So in here, you want to isolate the log. Then convert to exponential. Okay, that's all this technique is. So what's my logarithmic expression? It's this. It's natural log of x minus 1. So this is the thing I want to isolate. So I can do that by subtracting 2 first. I can just say 3 natural log x minus 1 equals 11 minus 2 is 9. Then I can divide both sides by 3 because it's 3 times natural log. And I get natural log of x minus 1 equals 9 divided by 3 is just 3. Now that you've isolated the log, you can convert to exponential. And you convert to exponential using that exact same thing. I'm going to scroll right back up to it. You use that rule, okay? Convert to exponential and use that to solve. So I see that the base of natural log is e. So it's e to the power of 3 equals x minus 1. You say ln has base e. Okay. So how do I solve for x? Well, add 1 to the other side. Therefore, x equals e to the power of 3 plus 1. And that's your answer. Because notice what the question asked. It said express your solution in terms of e and write an approximation using 3 decimal places. So we can go ahead and box this. That's our answer in terms of e. You can't do anything more with that, okay? Think of e just like pi. It is a number. But what is it approximately, right? Whenever I wrote that kind of double squiggle, that means it's not equal to, but it's approximated by. So we're just going to go to use a calculator real quick. E to the power of 3. Can I open the... Oh my gosh, there it is. There's my calculator app. Clear all this. Okay. E. Do you see this natural log button right here? Oh, it's so hard to put. Whatever. Look for the natural log button. If you click second natural log, you get E. Okay, and it says you could also do, it's on the division symbol. Second division symbol gets you E as well. We want E to the power of 3 plus 1. There it is. 21.0855. So let's say 0.086. So 21.086. That is the decimal approximation. But the exact solution is e cubed plus 1, okay? You may be asked to give the solution in either form, okay? You never know. All right, let's move on to the next example. Those two aren't so bad. They're going to start to get a little bit more tricky. Now, looking at example 3, we're going to start using the same base rule. This is a really simple rule, okay? I think it makes sense. I already explained it, but I'm going to re-explain it real quick. Look, if you have 4 to the power of x, and you say that that's equal to 2 to the x plus 1, right? Well, 4 is... These are different bases, right? 4 and 2 are different bases. However, 4 can be written as a base of 2 to some exponent because 4 is 2 squared. So if I do 2 squared to the x equals 2 to the x plus 1, then I say, okay, this is 2 to the, I multiply my exponents, 2x equals 2 to the x plus 1. Therefore, since the bases are now the same, the exponents are the same. So I say, therefore, 2x equals x plus 1. Solve for x. Let's say subtract 1x from both sides. I get x equals 1. And that would be my solution. And that makes sense, too, because 4 to the 1 equals 2 to the 1 plus 1. That says 4 to the 1 equals 2 squared, which is 4, which is true, right? I might jot that example I just did right there down in your notes because the example I'm about to work is way more complicated. And this example I just totally made off the cuff really just shows a simplistic idea of the same base rule. Okay, but I'm going to use this exact idea to do this problem. Now, let's look at our bases. I see a number 8, I see 1 over 32, and I see 4. And so here's what you know. You know that 2 squared equals 4. And you know that 2 cubed equals 8. You know that 2 to the power of 5 equals 32. So therefore, 2 to the power of negative 5 equals 1 over 32. I'm going to use these. Notice 4, 8, and 32. They could all be written with base 2. So I'm going to convert every single one of these pieces to base 2. So 8, that's 2 cubes. This is equal to 2 cubed times, I say 1 over 32, that's 2 to the power of negative 5. And this is raised to the x plus 1. And that equals 4, which is 2 squared, but that's being exponentiated by x plus 6, an exponent of x plus 6. Now you're going to use exponent rules. Do the exponent rule first. When I say exponent rule, I mean exponent to an exponent. in particular, I'm talking about this one and this one. If you're not sure what I'm talking about, it's where, oh my gosh, where is it? The power rule. Yeah, that's what I'm using right now. I'm using the power rule. I'm going to multiply those exponents together. So I'm going to get 2 cubed times, you see this is 2 to the negative 5 times x plus 1. Because that's the rule. When you raise an exponent to an exponent, the power rule says that you multiply those exponents together. Equals 2 to the 2 times x plus 6. If you want to go ahead and distribute that, you can. So I'll say this is 2 to the power of 3 times 2 to the negative 5 x minus 5. I'll zoom in so you can really see that. Equals 2 to the 2x plus 12. And now at this step, right here, you are multiplying to the same basis, so you add the exponents. So this is actually now 2 to the, 3 plus negative 5x minus 5, okay, equals 2 to the 2x plus 12. Of course, if you add that 3 there, that's just 2 to the negative 5x minus 2 equals 2 to the 2x plus 12. Okay? You know what I'm going to do? I'm just going to, I hope this doesn't take up too much time. I'm just going to lasso this real quick. I'm going to move this over here. I'm going to draw an arrow. Okay? All right. Now that the bases are the same, I say, therefore, negative 5x minus 2 equals 2x plus 2. And this is because same base rule. Okay, I don't even do parentheses. I'll just say by same base rule. I can make that conclusion. And this is a very simple equation to solve for x, right? Subtract 2x to the other side, you get negative 7x minus 2 equals 12. Add 2 to the other side, you get 14. Divide both sides by negative 7. I get x equals negative 2. Fantastic. X equals negative 2 is our solution. So see, all you had to do was manipulate the base and then use exponent rules to solve for x. There were no logarithms involved here, right? No logarithms whatsoever. You just use the fact that these happen to be able to be expressed with the same base. If they're not the same base, you can't do this. Okay, so if you got 2 to the x equals 3 to the x plus 1, you can't do this. You got to use logarithms somehow, okay, or something else. But you're not going to do same base rule for that. Okay, example 4, we're going to take the log of both sides. Now, I'm going to show you kind of 2 ways to do this, because here's the thing. You can choose the base of the log. This is up to you, all right? Think of it like this. You're going to take the log of both sides the same way you take square root. So like if I had 3 to the x equals 4, and I said square root of this, square root of that, right? I'm going to do the exact same thing by doing like log of 3 to the x equals log of 4, right? It's like I'm applying the log as an operation to both sides. That was what it means to take the log. And I'm going to show you 2 methods here. Now, I am going to go ahead and isolate the exponential expression. I'll say I will go ahead and isolate the exponential term. So to do that, I'll subtract 2 to the other side. I get negative 3 to the negative x minus 3 equals negative 2. Divide both sides by negative 1. This yields 3 to the x minus 3 equals positive 2. Okay? Now look, we could do the change this to a log and solve for x. You could do that. But what I'm going to show you is taking the log of both sides. It's a particular technique. Now, I'm going to split this into 2 methods. I'm going to say 1, take natural log. I say this is method 1. Take that. And again, you can choose anything, okay? I choose natural log most often because it's natural log. It's natural. It's my favorite log. I like the natural log more than any other logarithm. I like it more than base 10. I like it more than base 2. So I'm going to take the natural log of both sides, okay? So here's what this looks like. You have 3 to the x minus 3 equals 2. We're going to say natural log of 3 to the x minus 3 equals natural log 2. That is the taking of the log, right? That's taking the natural log of these things. Why is this useful? Well, the exponent is x minus 3, and the power rule, okay, I'm going to use log power rule. That says that log of m to the n equals n log m. Okay? You can pull the power out in front as a coefficient. That's one of our logarithmic rules. So this, if you look at the left side of the equation, is x minus 3. That's the exponent times natural log of 3 equals natural log of 2. Now, from here, if you divide both sides by natural log 3, I get x minus 3 equals natural log of 2 divided by natural log of 3. At this point, you can just add 3 to the other side. You say x equals natural log 2 over natural log 3 plus 3. And that's our answer. This one does also ask for a decimal approximation. We'll get there in just a second, okay? X equals natural log 2 over natural log 3 plus 3. Now look, you can use any log, guys, any. And if you use, like, let's say log base 10. If I do the exact same thing with log base 10, I'm going to get log 2 over log 3 plus 3. I will get the exact same result. And guess what? It's going to evaluate to the same number. It doesn't matter. Okay? I'll say, let's go up here. Let's say method 2. Choose a log using same base as exponent. Okay, so look, you've got 3 to the x minus. I'm just going to work the problem again. Okay? The base is 3. So base equals 3. So use log base 3. Okay, so if I take the log of both sides using log base 3, this is what that looks like. Okay, and now I'm going to use the exact same power rule as I did last time. Move x minus 3 out in front. I say log base 3 of 3 equals log base 3 of 2. But hey, guess what? Log base 3 of 3, the reason that we chose this log is because log base 3 of 3 is 1. So this equals 1, which means you have x minus 3 equals log base 3 of 2. Therefore, x equals log base 3 of 2 added with 3. And that is your answer. Okay? And by the way, this method, if you choose using the log of the same base as the exponent, it's actually pretty much the same as example 1. It's pretty much the exact same method. You're isolating the exponential and then converting to a log. Okay? It's actually the exact same thing. So why am I even bothering with this? And maybe I'll put this in red. Useful for calculus later. Okay? Method 1, where you take a natural log or take a log base 10. There are just some calculus problems that use it. It's just going to be nice, okay? If you are going to go into STEM, into math, and you know that that's your career option, I really highly recommend you try this and practice this now. That way when you take higher level math courses, you've already mastered this technique and you're fine. I may ask you to demonstrate this skill on a assignment, but this is a way to do it. It's not the way to do it, okay? This is how I normally solve stuff, though. I usually take the natural log of both sides. Extremely useful. Extremely useful. Now, we never got our approximation here. All right, so both of these, right? What is the approximation? X equals, well, here I'm going to show you. Natural log of 2 over natural log of 3 plus 3. We're going to go to the calculator. We're going to say, we're going to make a fraction. We're going to say natural log of 2 over natural log of 3 plus 3 is 3.631, a nearest hundredth. So I say 3.63. Check out your other answer, log base 3 of 2 plus 3. If I go to, it's math, log base of 3 of 2. Is that right? Log base 3 of 2 plus 3. Look at that. It's the same number. So both of these answers are correct. They are different ways to write the exact same answer, and that's fine. But I'm going to emphasize, I really like method 1. I really like taking natural log or log base 10 and not fiddling with different variety of bases. Just trust me in the long run, okay? Okay. I know that the video is probably getting a little long, so I'm going to try and hurry it up, but we've got 2 more to talk about, okay? And they're getting harder. All right. So, example 5. Solve using factoring patterns. So we're going to solve this exponential equation. We're going to write this solution in calculator-ready form and give the approximation here to the nearest hundredth. So calculator-ready form means expresses a log, okay? That means express as a log. That's all that means. Whatever logarithm you got to use, okay? So let's do this. How in the world are we going to approach this? I'm just going to show it to you now. And you try, for right now, you try to make sense of it. And if you do not get it, ask me in class, okay? If you do get it, hooray, you understand. So 4 to the power of x, 2 to the x plus 3, plus 5. I'm going to have fun with this. I'm going to manipulate it. Well, 4 could be written as a base of 2. So I'm going to say that 4, this is actually 2 squared to the x minus 2 to the x plus 3 plus 15. Okay, that is true. And if I use power rule for exponentials, I multiply those. It's 2 to the 2x minus 2 to the x plus 3 plus 15. And actually, well, a couple of other things here. If it's 2 squared to the x, you can actually rewrite this also as 2 to the x squared. Okay? And then I'm going to say this is minus. Now, see, this says if it's 2 to the x plus 3, well, I can split that up as 2 to the x times 2 to the 3. So this is actually 2 to the x times 2 to the 3 plus 15. You know, I'm gonna leave this step as this. I'm gonna do that in the next step. Now, what is 2 to the power of 3? It's 8. So look, 2 to the x squared minus 8 times 2 to the x. Maybe I'll put this in parentheses. Plus 15. So you see how I've kind of manipulated this, right? I've just played around with the exponents and fiddled around here. That is factorable like a quadratic. Let me show you. Let u equal 2 to the power of x. Then 2 to the power of x squared is u squared minus 8 times 2 to the power of x is u plus 15. Look at that. I'm going to move this up here. So how does this factor, right? I guess this should have been equal to 0. Sorry, this is equal to 0. So all of these should say equal to 0, equal to 0, equal to 0, equal to 0. This equals 0. So now I have u squared minus 8u plus 15 equals 0. This factors as, what is that, u minus 5 and u minus 3. So therefore, u equals 5 and u equals 3, right? But what is u, right? What did I say u was? Since u equals 2 to the x, then 2 to the x equals 5, and 2 to the x equals 3. Now, convert to log. Log. Therefore, I say, therefore, x is equal to log base 2 of 5, and x is equal to log base 2 of 3. Done. Nice. And those are your answers. Okay? You could also express them as natural logs if you'd like, but I just did a simple conversion to log, and those are the solutions to the problem. Finished. This is factoring like a quadratic. You manipulate the exponential equation to look like a quadratic one, do a sort of substitution so that you see that it looks just like a quadratic, and then you can put back what you substituted in and solve using a logarithm. Okay, so that's my answer. I did ask for an approximation, so I'll say x is approximately log base 2 of 5. Let's go over here. Math. Log base 2 of 5 is 2.32. Okay. 2.32. And x is approximately log base 2 of 3. Log base 2 of 3. 1.58. 1.58. And those are my beautiful solutions. Done. Okay. Example 6. Get creative and use everything you know. So who knows? You can use a variety of techniques here. I'm going to show you something fun. Okay, so let's solve this logarithmic equation and give an exact value for x. So we're not actually going to use a calculator. When I say give an exact value of x, we're going to use either a logarithm or maybe we have a base. Who knows? We're just going to give it in like calculator ready form. Okay, I'm going to use logarithmic properties here to combine these logs. You see, I've got two logarithms, right? Log base 3 of x, log base 3 of x plus 1. So power rule says that, right, this implies that this is log base 3 of x squared. This comes from the logarithmic power rule. And this is minus log base 3 of x plus 1 is equal to 0. Now, since they're the same log, they're both log base 3, here I'll say by power rule. By power rule of log. And now for the next one, I'll say by the quotient rule. Quotient rule of log. You can put these together and say that this is log base 3 of x squared divided by x plus 1 equals 0. And now what's happened here is I have a single isolated logarithm. Now I can convert to exponential. I say that 3 to the power of 0 equals x squared over x plus 1. But of course, 3 to the power of 0 is 1. I'll multiply both sides by x plus 1, so it's 1 times x plus 1 equals x squared. So I've got x plus 1 equals x squared. Let's move this. Just move this over here. You say x plus 1 equals x squared. Subtract everything to one side. So x squared minus x minus 1 equals 0. Ask yourself, is that factorable? No, it's not factorable. So how could you solve it? X equals negative b plus or minus the square root of b squared, negative 1 squared, minus 4ac all over 2a. Oh, yeah. If you can't factor, use quadratic formula, right? Or complete the square if you like, which I actually prefer, but whatever. You guys hate it. I don't know why you hate it. You shouldn't hate it. You should love it with all your heart and being. Here we go. 1 plus 4 over 2. So this is 1 plus or minus root 5 over 2. Boom. That's the answer. I say, therefore, x equals 1 plus or minus root 5 over 2. That is the solution to this problem. Finished. Okay? So this problem, we used a few things. We used the properties of logs to combine to a single logarithm. We converted it to exponential form, and then it became something we were very familiar with. It was just a quadratic that we could use quadratic formula on. And that's it. Okay. All right. I'm sorry if this video was a little bit long. It's okay if you didn't make it through all of it tonight. It's okay. I understand. Okay. I'm sorry I made it so long. But we got to talk about this. It's a lot, right? It's a lot of stuff. And I did not want to do all of this in class. So In hindsight, maybe I should have only done half of this video and then save the other half for class. We will talk about these last 3 examples a lot more in class, okay? Okay, thanks for watching. Have a good night, and I'll see you later.